So now that we have an overview of cellular respiration, let's look at the first stage that we can see when we are following a glucose molecule to be harvested for energy. So again, the three stages of cellular respiration are going to include glycolysis, citric acid cycle, or the TCA cycle, tricarboxylic acid cycle, also known as the Krebs cycle, and oxidative phosphorylation. Again, this is following a sugar molecule, but you can feed, and we'll look at this at the end, you can feed fat and protein into somewhere in this biochemical pathway to generate ATP as well. So you can break down things other than sugar and do. So glycolysis is going to take place in the cytoplasm. Right? So we can see this mitochondria here in this pink square. That's going to represent everything outside the mitochondria. So we know the mitochondria are inside the cytoplasm of the cell. So all this first step of breakdown is all going to be enzymes in the cytoplasm addressing a molecule, glucose. All right. So glycolysis literally means splitting of sugar. Lysis, to break something. Glyco, sugar. We're going to break it down ultimately into two molecules of pyruvate. And so you might say, well, I don't know what pyruvate is. What is pyruvate? It is a 3-carbon carbohydrate that you can break a glucose molecule into two of them. And so you need to become as familiar with that as anything else. And so we're going to say it again and again. So pyruvate is going to be the main product that we're interested in from glycolysis, because that's what's going to go on to be oxidized even further to ultimately make more ATP. Now, glycolysis is going to occur in two phases, an investment phase and a payoff phase. So because this is occurring in the cytoplasm, we've got pools of resources, but realize that the net result of glycolysis is a gain in ATP and a gain in NADH and a gain in pyruvate. Right? So if you see the whole process here, which we're going to go through step by step, we have an investment up top. See glucose, step 1, ATP is expended to add a phosphate group. And step 3, you're going to expend another ATP, ATP to ADP. But as we move then down further in the process, we start to gain energy molecules. We're going to get NADH out of there, which we'll talk about in just a few minutes. And you start to get ATP out. So you get 4 ATP total with the investment of 2. So there's a net gain there. And that's really important because we have to think about the big picture here. These are all linked reactions, right? Now, again, here's another way to look at that. We see an investment of 2 ATP in the early stages, and then we get 4 ATP back, and 2 NADH, and 2 pyruvate. Right? So again, we have a net gain of energy from this process. So where does this process start? We're going to look at the carbon molecules, and it's very common in metabolism, especially catabolic reactions, to follow the carbons. Right? So are we going from a 5-carbon molecule to a 6-carbon molecule to a 4-carbon molecule to whatever it may be? All right? So in this case, we're going to start with glucose, which is a 6-carbon molecule. And the first step is the activity of hexokinase. And in this case, we're going to phosphorylate this molecule to make glucose 6-phosphate. This is the first step. I've added energy. I've gotten nothing out of this yet. Then we're going to hand off the product of the first step of hexokinase to phosphoglucoisomerase. And this is going to rearrange the molecule into fructose 6-phosphate, which is going to be prepped then with phosphofructokinase. So we're going to take fructose 6-phosphate and add another phosphate onto it, fructose 1,6-bisphosphate. Again, the numbers are referring to the carbon atoms, right? So fructose 6-phosphate says, oh, I've got a phosphate attached to the 6th carbon. Fructose 1,6-bisphosphate, fructose carbon base molecule. On the 1 carbon, I've got a phosphate, and on the 2 carbon, or on the 6th carbon, I've got a phosphate. Bis by 2 phosphates. All right. So fructose 1,6-bisphosphate. And that's why we're going to go through each of these steps. You do not have to know each of these steps. You do not have to memorize glycolysis. But I do want you to use the terms and get familiar with them, and I'm going to really encourage you to do that with the activities that we're going to do with this topic. Now, fructose 1,6-bisphosphate, we've gotten nothing back from this yet. We've only invested in it. And as we've invested in it, we've really primed the free energy of this molecule. And so this now is a good control point. I want you to remember that with fructose 1,6-bisphosphate. This is where we're going to break it down now into two 3-carbon molecules. So aldolase is going to break this down into dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. And isomerase is going to convert dihydroxyacetone phosphate into glyceraldehyde phosphate because the G3P, that's the shorthand for glyceraldehyde 3-phosphate, is going to move further down the biochemical pathway. And as long as I keep drawing that off, the equilibrium for the isomerase will always be pushing towards G3P. And so we're going to be always drawing off the dihydroxyacetone phosphate to feed into G3P. G3P is being then fed into triose phosphate dehydrogenase, right? And now we're starting to get energy out of the system. So now we're getting our return from our investment as we convert NAD to NADH. Now NADH is you want to think about it as a high energy electron carrier, and we'll look at that structure before we're done. But for now, realize, just put it on the back burner and say, okay, that's energy that I'm going to use later to make ATP, and it's a shuttle, right? I'm going to carry this into the mitochondria and ultimately use that, like I said, to make ATP. So we go from glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate. All right. This molecule then is processed by phosphoglycerokinase into 3-phosphoglycerate. Boom! Another return. So now here we get ATP out. Now remember, again, for every 1 glucose that we put in, we split it. And so now you see that we have 2 1,3-bisphosphoglycerates. And so I get 2 3-phosphoglycerates. From each one of those, I get an ATP. So this is where I get 2 ATP back. All right. Now, 3-phosphoglycerate then is processed by phosphoglycerylmutase, and we get 2 phosphoglycerates. That then is processed by enolase, and we get phosphoenopyruvate. There's the pyruvate. Okay, it's a modified form of pyruvate. We're getting close. And then finally, pyruvate kinase is going to get our other 2 ATP out, one from each of the molecules of phosphoenopyruvate that we have, to get 2 molecules of pyruvate. There we go. So that process is incredibly old. Most bacteria have that biochemical process, as do you. So this is a very, very old biochemical pathway, and what we're getting is pyruvate. That's what pyruvate looks like. You should be familiar with that. It's a very, very important molecule. So again, the yield of glycolysis is 2 ATP net, 2 NADHs, and 2 pyruvates. Now let's focus on those 2 ATP. We know ATP is our high energy molecule, but we produce these ATP by what's called substrate level phosphorylation. Literally, I took an ADP and forced a phosphate group from a substrate onto the ATP, onto the ADP to make ATP. So this is literally an enzyme being like, I'm going to take this phosphate over here, and I'm going to force it on there based on the energy change from the reactants to the product. Okay. So this is kind of a 1-for-1. From one substrate, I get 1 ADP. And we're going to contrast this then with oxidative phosphorylation later in the process of cellular respiration and see that the yield that we get from oxidative phosphorylation is much, much higher. Right? Not that this isn't important. It is. And when you can't do anything else, this is what you do. But that's why I'm bringing it up. So this is substrate level phosphorylation. All right? And again, we can see that occurring in the latter half of the glycolysis pathway. All right? And there we're getting 2 back. Now, the other yield of glycolysis is NADH. So let's take a second here and look at NADH. So NADH, and in this case, a nicotinamide adenine dinucleotide, is going to be our electron carrier. Right? So this is really the process. You have this big molecule, but ultimately what you're looking to do is just attach an electron onto that molecule so that it can carry it, and it's a high energy electron. It's an electron that I want to give to another molecule that I can easily reduce something else. So this is a very, very effective reducing agent. It's reducing power that we're building in NADH. All right, and that will come into play later. So we're getting our NADH at the glyceraldehyde 3-phosphate stage, step 6 in glycolysis. It's our return stage. Okay? So again, this is a stepwise harvest of energy. So we're going to use NADH as an electron shuttle, and we're going to see how that fits in later to make ATP. Now, finally, we have 2 ATP, 2 NADH, and those 2 pyruvate. Pyruvate is what we're going to focus on now because we're going to take those 2 pyruvates. Each has 3 carbons, and those carbon-carbon bonds have lots of energy that we're going to kind of extract now in a stepwise manner in what's called the Krebs cycle, or the tricarboxylic acid cycle, or the citric acid cycle.